Hi, in this video we're going to look at interpreting a derivative. Alright, so we're given a function here. We've got a population whose growth can be modeled by this equation. T is given in years since 1950. P is thousands of individuals, and we're asked to find and interpret some values for the function and its derivative, and then also some limits for the function and its derivative. So just to keep my work organized here, I'm going to first of all find the derivative, and then I'm just going to make a chart so we can evaluate both the function and its derivative and interpret those. Okay, so when I look at my function that I'm going to start with, and I'm going to think about finding the derivative, the first thing that I might notice is that there's actually only one place that there's a t in this equation in the input. So although I could use quotient rule, it's probably better if you realize that you don't really need quotient rule to find this derivative. If I rewrite this function as 300 times this whole denominator to the -1 power, then I can really just use chain rule to do that. Alright, then when I find the derivative, p prime of t, I'm going to bring down the exponent and multiply that times my 300 that's out front. And then subtract 1 from the exponent. And then I need to take that times the derivative of what's inside here. So the inner function here is all of this inside my -1 power here. So when I'm doing chain rule here, I take it times the derivative of what's inside. I'm going to be taking this times the derivative of what I highlighted in yellow. Okay, so the derivative of 2 is 0. I don't really need to write that derivative down, but and then the derivative of 13 times e to a power will be 13 times e to that power times the derivative of what's inside that power. Alright, so I actually used chain rule twice there. Alright, so there is my derivative. Since I'm going to plug some numbers into it, I might want to go ahead and clean that up a little bit. I have a whole expression to the -2 power, so I'm just going to put that on the bottom of my fraction here. And have that squared. I don't really need to write this 0 that's here. So I'm going to get rid of that, and then the rest of this stuff here is going to be on the numerator and times each other. I have a negative times another negative, so that'll be a positive on the numerator. And then if I multiply 300 times 13 times 0.06, I get 234. And then I'll have e to the -0.06t. And while you don't have to do that simplifying, since I'm going to be plugging some numbers in here and thinking about a limit, it might be easier to do that. Okay, so I'm going to scroll up here and make a little chart. I've got several different t values to plug in, 0, 10, 60, and 100. And then I'm supposed to think about what happens as t approaches infinity, both for the original function and its derivative. So we're going to just make a little chart. Alright, so I'm plugging t equals 0 into the original function, so I'll have 300 over 2 plus 13 times e to the 0 when I plug in t equals 0. So e to the 0 is 1, so I end up with 300 over 2 plus 13, so 300 over 15, and that comes out to be exactly 20. Exactly 20. Alright, so remembering that what it said in the original problem, I'll scroll back up here. Our population P is given in thousands of individuals, and T is given in years since 1950. So the interpretation of what this number means is that when t equals 0, or in 1950, the population was 20,000 individuals. Alright, so all of these p values are going to be population at a particular time. Okay, thinking about the p prime of t, I'm going to plug t equals 0 into my p prime function here. So I'll have 234 times e to the 0 over 2 plus 13 times e to the 0, the quantity squared. Okay, so when I simplify that, I get 234 over 2 plus 13 is 15 squared. And so when I simplify that, it doesn't come out exactly, but we're going to use some decimal approximations here. So I'm going to write is approximately equal to 1.04. Okay, so one of the key ideas here is to remember that a derivative is a rate of change. And so this tells us something about how p is changing. Since this is a positive rate of change, this tells us that p is increasing, going up, a positive rate of change, getting bigger by this number, 1.04 units of whatever p is. That would be 1,000 individuals per unit of input, so that would be per year, in the time when t equals 0, so in 1950. Okay, so we could say that the population is increasing by 1.04 thousand individuals per year in 1950, or we could simplify that a little bit. Instead of 1.04 thousand, that would be approximately 1,040 individuals per year in 1950. So that tells us how p is changing. So this is really about a rate of change, and that's really the emphasis of section 3.4 in our textbook, is understanding a derivative as a rate of change. Okay, so for these others, I'm not going to write out the plugging the number into the formula. We'll just look at the result that we get. So p of 10 is, these are all going to be approximately 32.842. 32.842 when you plug t equals 10 into the original function p function. So again, the original function gives us a population, and this is in thousands of individuals, so 32.842 thousand, or 32,842 individuals when t equals 10, which was in 1960. The other part here that we want to think about, and kind of the new part here, is what does the rate of change mean? When I plug t equals 10 into my derivative function, I get approximately 1.539. So what that tells us is that the population was increasing. That's a positive rate of change, so increasing by about 1.539 thousand, or 1,539 individuals per unit time, so whatever the units of input are, in this case it's years, in 1960. So in 1960, this population is increasing more rapidly than it was in 1950. So we think about that as a slope of a tangent line, a steeper curve, a larger rate of change. Okay, when we plug in t equals 60 into our population function, we get approximately 122.377 when we plug that into the population function, p of t. So remember that the p is measured in thousands of individuals, so the population was approximately 122,377 individuals when t equals 60, and 60 is years since 1950, so that would be in the year 2010. When I plug t equals 60 into my p prime, I get approximately 1.153. Or interpreting that, that tells us that the population, again, a positive rate of change, so it's increasing by 1.153 thousand, or 1,153 individuals per year in the year 2010. So rate of change. And one thing that would be important to notice is that that rate of change has slowed a little bit. So it was increasing pretty rapidly in the year 1960, and the rate of increase has slowed a little bit and in the year 2010. All right, so t equals 100, that would be 100 years after 1950. So these are going to be predictions. T equals 100, we're going to get approximately 147.622. So what that would mean is that the population is projected to be, this is in the future, 147,622 individuals when t equals 100, or 100 years after 1950, or in the year 2050. All right, p prime of t, when I plug in t equals 100, we're going to get approximately 0.140. All right, so interpreting that again is a rate of change. So that is saying that in the year 2050, or 100 years after 1950, the rate of change, or the rate of increase of the population, is projected to be 140 individuals per year. Okay, so the rate of growth has really slowed there, and those other ones we were looking at, it was growing by at least 1,000 individuals per year, and now it's really slowed to 140 individuals per year. Okay, the last thing that it asks us to look at here is what happens as t approaches infinity. So I want to go back up and look at my population function, the original function that we were given, and I can also look at my derivative function and think about what happens to those functions as t approaches infinity. And so you can look at that graphically, you can look at that numerically, you can think about theorems with that. I'm going to think a little bit with theorems for p of t, and then we'll look at, for p prime of t, we'll look at thinking about that numerically. For p of t, let's go down here and look at this function. So we're going to think about the limit as t approaches infinity of our original population function. I'm going to write it like it was originally given in the problem, 300 over 2 plus 13e to the negative 0.06t. And I'm going to think about what happens when t gets large. Okay, so when t gets really large, this is an exponential decay function. I've got a negative exponent here. So the e to the negative constant times t function, that will approach 0 when t gets really large. And so on the overall function, that limit is going to approach 300 over 2 plus 13 times 0, or 300 over 2, or 150. Okay, so interpreting what that means that long term, this population should approach, it may or may not equal that value, approaches 150,000 individuals. What the value of p is going to be when t becomes really, really large. Okay, and then this other interpretation, we can think about that numerically. So I might think about in a table just plugging in very large values of t into the p prime function and look at a table and see what you get for that. So when you get that, you're going to get some values that are very, very close to 0. When you put large values of t into the derivative, you can also think about that using theorems or a graph of the derivative, but thinking about the values of that p prime when t gets very large. And so the outputs of that actually approach 0. And maybe we could kind of see that happening if I think about these rates of change for these other things here. I had a population that was increasing pretty rapidly and then slowing a little bit. And then what happens eventually when t gets really large is that that population rate of change is going to approach 0. The slope of the tangent line will approach 0. So we could say there that the population eventually really stops increasing and stabilizes so that it has really a 0 rate of change. If you look at a graph of the overall function, you might have to play with the window a little bit, although some of the values that we've plugged in might help you with that. But what you should see when you look at a graph like that is that you should see that you have a function that's growing pretty rapidly at first and then levels out. And then if you look at that as t grows larger and larger and larger, you'll see that you've got a horizontal asymptote at 150. And the slope, that graph is getting very, very flat there. The slopes of those tangent lines, as you go out there, the slopes of those tangent lines is approximately 0. So there's an approximately 0 rate of change as you go far out on the right side here. So the function output values are approaching 150 or 150,000 individuals, but the rate of change, the slope of that tangent line, is approaching 0.